We have about three or four more classes, I suppose. Anyway, we're talking about compactness. Last time we did a bunch of examples about compactness, and remember, I will just refresh our memory about the definition. So a set A is compact. Anybody want to shout it out? What does that mean? Nobody wants to shout it out. I will proudly stand and say what compact means. I'm sure somebody must remember.
Open cover is a finite subcover.
Yes, A is compact when any open cover of A has a finite subcover. All right. I would say, and last time we did a lot of examples, hopefully to give you some kind of intuition about what sort of sets are compact and what sort of sets are not compact. I would say my general intuition is that compact things, well, how about, this is a little vague, but generally speaking, sets which omit some boundary points or stretch out to infinity are not compact. If you recall from last time, the examples that we were doing, a lot of them had to do with this. If there are some boundary points missing, then you can make an open cover that kind of approaches the boundary, but never quite reaches the boundary, and then that you can use that open cover which approaches but doesn't reach the boundary. That will not have a finite subcover. That's what most of the examples we talked about last time were like that. So sets which omit some boundary points or sets which stretch out to infinity, they are automatically not compact. If I have a set, say in R2, which goes all the way out to infinity, then you can make little balls that cover it, but you can't use only finitely many of those little balls because it goes out to infinity. So this is a general principle. Sets which omit some boundary points or stretch to infinity are not compact. Actually, if you believe me when I'm saying this, let me say the opposite then. So a compact set, this is still speaking sort of in generalities, I mean in somewhat vague terminology. A compact set should include all the boundary points so that you can't do that trick where you make the open cover approach but not reach the boundary. A compact set should include all boundary points and not stretch to infinity. Nah. All right, this is the intuition that we were talking about, or I hope that you were thinking along these lines. And actually, if you translate this into more technical language, include all boundary points, that means closed. And not stretched to infinity means bounded, right? So this should look familiar. This is the Heine-Borel theorem from analysis. Says that in R, at least, this is actually a theorem, that a compact set is closed and bounded. That is a theorem in R. It's actually not true, more generally speaking. In some other weird topological spaces, this kind of thing is not always true. But in R, at least, that is true. So this all of this, like intuition and the examples that we were doing before, this all works great in R, or actually in more generally in Rn. This Heine-Borel theorem is actually true even in R2 or R3 or whatever. But weird things, I'll say this all works great in Rn and similar. For example, if you have a metric space, then a lot of this will work, even if it's not necessarily Rn, but you still have a distance kind of a thing, then this sort of stuff can still work. And we're going to get into that a little bit in the future. But for today, I want to talk about some other settings. So I'll say all of this, what I said, works great in Rn and similar spaces, but weird things can happen in weird spaces, right? If you have, for example, a topological space that's not Hausdorff, then some strange things can happen. For example, you can have a compact set that's not closed. So that's the kind of stuff that I would like to talk a little bit about today. I thought we'd start off with a easy, and actually this is not so weird, but this is a simple little theorem here, which I would like to hear your input about. It says that in any topological space, if A is finite, that means it just has a finite number of points, like 3 points or something like that. If A is a finite set, then A is compact. Every finite set, no matter what, is always compact. Let's see if we can do the proof of this. The picture you should have in your mind is A as a set. It looks like that, maybe. Just 4 points or whatever. 5 points. 500 points. It doesn't really matter how many, but it's a finite amount of points. All right? And then, so let's see if we can write this proof. So we must show A is compact. That means we have to show that any open cover has a finite subcover. So you should begin any proof like this about something is compact. We should begin by saying let O be an open cover. All right, and then we'll show, I want to show that we can find a finite subcover. All right. So on my picture, what does O look like? An open cover is just some big bunch of open sets which cover up all of those points. So now, not all of the open sets actually hit those points. They don't have to, at least, but eventually all of those open sets cover all of this stuff. Something like that, right? That's my open cover. And the open cover that you assume exists might not be finite. That's the thing. It could be infinitely many sets in this open cover. But I ask you, is it possible to use only finitely many of these sets to still cover all the points? Or do you really need all infinitely many of them? I think you do not need all infinitely many of them. Actually, in this picture, how many do you need? I would say 4. Yeah, you'll only need 1 for each of those 4 points, right? How do you know for sure that there actually is 1 around each of those 4 points? Well, that's because this is a cover, right? That means actually it does cover up those 4 points. And so I can just choose 1 for each. So that's all we need to say for this. So I want to show we can find a finite subcover. Maybe just to, like, it's a very simple idea, maybe just to say specifically the details here. It might be helpful to give a name to these points. I'll call them like A1, A2, A3. On my picture, there's just 4 of them, right? So I'll say let A, since it's finite, I can write it like this, A1 dot 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 AN. It just has a certain number of points in it. And because O is a cover, that means there are actually sets, there are neighborhoods around each of these points. So since O is an open cover, each point there is in one of those open sets. So maybe I'll say there are sets U1, blah, 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 UN. And these are from O with, A1 is in U1, etc. AN is in UN. I'll just say AI is in UI for each I, right? So we have only a certain number of points. Each of those points comes with a little neighborhood around it from the original cover. And then, I want to show we can find a finite subcover. Well, that's what it is. It's those little neighborhoods that we chose, 1 around each point. That makes a finite subcover. All right. So there are these U's, and then if I just consider those together, U1, UN, this is a finite subcover. There you go. If you have only finitely many points, then you can always cover them with only finitely many sets. That's how it goes. Any questions about that? So this is a very simple case in which any this is true no matter what. Any finite set is always automatically compact. Excellent. What about infinite sets? Well, some are compact and some are not. We already saw last time that, for instance, like the closed interval in R, closed interval 0 to 1, for instance, that is compact, even though it is an infinite set. It's not unbounded, but it's still an infinite set because there's infinitely many points in there. So I would say some infinite sets. For infinite sets, you can't say really. Some are compact, some are not. All right. Welcome. Hey, everybody's here. That's great. Some are compact, some are not, if the sets are infinite. Okay. I would like to talk about one other simple situation. I would say this one where the set is finite is a simple situation. I kind of wrote a lot of words here, but I hope that you agree that the idea is very straightforward. What about another situation which is fairly simple? Is about if I have a topological space with the discrete topology. In that case, any infinite set is not compact. If you're using the discrete topology, then all infinite sets are not compact. So for this one, we would have to find an open covering which cannot be shrunk down to using only finitely many sets. So let's see what we can do with this. This one also has a simple idea, although it's a little weirder just because it's the discrete topology. But I'm going to say let A be a subset of X be infinite. And then we're going to show that it's not compact. So I'll say want to show A is not compact. What that means is you need to find an open covering with no finite subcover. So I'll say i.e. I want to show there's an open cover of A with no finite subcover. And this you have to be a little bit creative about because you're not really given anything to work with in terms of hypotheses other than the fact that A is an infinite set. So maybe I will try to draw a picture of A as just like a bunch of points, infinitely many of them. And we're using the discrete topology, which is why I drew them as if they were kind of separate from one another, because in a discrete topology, none of these points are inside of the neighborhoods of the other ones, right? That's how the discrete topology works. And we want to show that there is an open cover with no finite subcover. So you have to build your open cover from scratch. Anyone want to, knowing what you know about the discrete topology, I would like to use sets that cover the whole thing like what? Anybody got any ideas? I would say if I was like talking about in R2, I would use little balls, right? That would be appropriate in R2 with the standard topology in R2. I use the R2 balls. But I'm talking about some kind of thing with the discrete topology. Anybody have feelings about the discrete topology? Perhaps think about what's your favorite little neighborhood to use in the discrete topology? Yeah?
You just use a point.
Yeah, your favorite neighborhoods to use in the discrete topology should be individual points themselves. They are open sets by themselves. All right. So in this case, the sets I'm going to use are actually just those individual points. So I use sets like, you know, that for A in my set. Choosing only individual points by themselves. Usually that's not an open set, but in the discrete topology, those are open sets. That's what a basis for the discrete topology is, individual points, right? Okay, so if I use sets like that, so if you want to be really technical about it, this looks a little weird, but O is defined to be the set of all set of A, where A is in A. That's my open cover, right? It's the set of all single point sets. This is an open cover. Open because I'm using the discrete topology, which means individual point sets are open. And can I make a finite subcover here? The answer is no. Maybe can someone explain why? You could think of these as just, you know, these points by themselves are my open sets. Is it possible to use only finitely many of them and still cover the whole thing? I see some people saying, no, it's not. Why is that not possible? I say, yeah, because A is infinite. There's infinitely many points in A. And so if you want to cover it up with single points one at a time, you're going to have to use infinitely many single points one at a time to cover it up. So this is an open cover. I'll just say, but has no finite subcover. Since A is infinite. I lost my train of thought for some reason. This has no finite subcover since A is infinite. You're covering it by one point at a time, so it must be, you're going to have to use infinitely many of them. All right, great. So in the discrete topology, infinite sets are not compact. Finite sets are compact. That's true all the time. All right. Excellent. I got one more, and then we'll talk about something slightly different. So I would like another somewhat weird example. This is the discrete topology, which is slightly weird. How about our old friend? We haven't talked about this one in a while, but how about in R with the finite complement topology? Remember this one? This means the open sets here are sets with finite complement. So remember, this means an open set is like all points except for a few omissions. It has all real numbers in it, but it's leaving out just finitely many points each time. All right? In this one, it turns out in R with the finite complement here, oops, maybe I'll write this as a theorem also. In R with the finite complement topology, all sets are compact. This is very weird. They don't have to be closed. They don't have to be bounded. It doesn't matter at all. Just every set in the finite complement topology is compact. Let's see if we can demonstrate that. That means every set has, no matter what open cover you use, it always has a finite subcover. So I'm going to say, you know, let A be a subset here of R, the finite complement, and then let O be an open cover, and then we'll find a finite subcover. This is actually one of the homework problems in the book, which I was thinking about making you do for the homework, and I thought, let's just do it in class. All right, so A is a subset in the finite complement. So the picture you should have in mind is A doesn't have finite complement. A can be whatever, right? A is just any set. And then we have an open cover of A, the cover has to be open sets, which in the finite complement topology look like this. All right, so that's A. If I were to write out, maybe I'll just try and draw a picture of what my open cover sets look like. Remember, in the finite complement topology, an open set looks like everything with finitely many omissions, right? So something like that. And then maybe my next one, I just have a bunch of sets that look like this, that cover up A, all right? And these sets do cover A, don't they? Actually, I think those two sets already cover up all of A on my picture at least, because every point from A is in either one of those. But anyway, that's what the O is. Maybe one of these is only missing one point over here. Maybe another one is only missing that point over there, etc. Right? That's what the sets in my open cover look like. Now, we have to somehow argue that you don't need all those sets. You only need finitely many of them, no matter what. Now, if you look at my picture, and probably whatever you drew, it is also satisfies this property. That actually, on my picture, if you think about it, even the first set almost totally covers A, right? And this is not because my A looks like that. Actually, the first set, it just almost totally covers everything in R, right? It only misses finitely many points. And so, it so happens that this second set fills in those missing points. Like the first set here is missing that point from A, but that point is in the second set. So can we somehow argue that this will always work out fine? I would say my basic idea is the first set already almost covers all of A, right? So I'm going to just, now O could be infinitely many things here. Let's just choose one of them and call it like the first set. So I'm going to just choose any, I'll call it like U0 in the open cover. And imagine that's like what I'm going to start off with. And already U0 covers almost all of A. In fact, it must cover all of A except for finitely many points, because it covers all of everything except for finitely many points. So choose any then. I'm imagining this. I just picked that first one as my U0, all right? And I will say U0 already covers, sorry, my pen is messed up here, already covers all of A except finitely many points, right? Because that's what a finite complement open set looks like. It covers everything except for finitely many points. So U0 by itself already covers all of A except for finitely many points. Basically what I need to do is choose some more sets just to make sure we plug in all the points that got missed by this first one, U0. Is it possible to do that choosing only finitely many more sets? I think it is possible, because this one only misses finitely many points, right? So if I have, say, 3 points missing after I take the first one, I can find 3 other ones somewhere that fill in those 3 individual points, and that should do it, right? So U0 already covers all of A except for finitely many points. That's just to be specific about this. Let's say that A, I meant U0. Let's say U0 covers A except it misses, A1, A2 to AN. So on my picture, like this is like A1, this maybe is A2. Those are 2 points that got missed from A by the first set. But in this case, those are only 2 points. That means I can just look somewhere else and find one that does cover this point and find another one that does cover that point, and I'll be done with only 2 extra sets, right? So let's say it covers everything except it misses those, and then kind of like before, I can just say we can find sets U1, UN that just kind of like plug in those missing values. We can find these with A1 is in U1. These come from the open covering. AN is in UN. Because every point is covered by the covering, you can find some open sets which which plug in the missing values that you want. And so altogether, those sets cover the whole thing. And there's only finitely many. There's really U0 and then U1 through UN. And so U0, U1 up to UN is a finite subcover. The first one gets you almost all the points. To cover the rest of them, you just have to choose a few more, finitely many more. All right. So all sets in the finite complement topology are compact, right? I will just remind us. Any set is compact, and I will just say specifically even unbounded sets and even not closed sets, right? So that theorem about compact is the same as closed and bounded, that's not true all the time. It's not true in this RFC. It's only true in, well, it's true in Rn and some other situations, but it's not generally true in all topological spaces. All right. We got about 20 minutes. I had two important theorems to discuss about compact sets in general. And the first one, I thought we could work together on this. You know, sometimes I always am looking for ways to do things differently than me just like telling you stuff and you listening. I thought maybe we could try and work on this on our own, and with the nearby Julia. What I would like to talk about is a similar theorem to we had this theorem for connected sets, was that it's about this, right? If I have A here and a continuous function and turns it into F, well, we called it X. In this situation, if X is connected and F is continuous, then the image over here is also connected. This is a basic fact about connected sets and continuous functions, and this is basically the same as the intermediate value theorem from calculus, if you're talking about subsets of R. The same is true for compact sets. So if F is continuous and X is compact, then F of X is also compact. This is a true fact, and this is what I want to talk about. So I'm going to write that as a theorem. If X is compact and F going X to Y is continuous, then F of X is compact. This theorem also is basically the same as a well-known theorem in calculus, and we'll talk about the connections. This is a little bit more complicated than the one for connectedness, but we'll talk about the connections maybe next time or some other time. But anyway, if X is compact and the function is continuous, then F of X is compact. So here, I thought this is going to be my strategy. I would like you to see if you can make some progress on this. I'm going to walk around and see how you're doing. And every time I see somebody write something good, like the next correct step, I'm going to come up here and write it on my screen. So you can catch up with your friends if somebody else has a good idea. And hopefully we will eventually come up with a complete proof here. So maybe I'll just get us started. I'll say, you know, let X be compact. And then we want to show F of X is compact. Anybody want to get me started here as far as a general structure here? What should I do to show that this is compact? We've done this in previous examples. Compact means any open cover has a finite subcover. So. Yeah, we need to show that every open cover has a finite subcover. So you say, I would say something like let O be any open cover. And then I want to show there's a finite subcover. And you have to use the fact that it's continuous. That's the thing that's going to make this work out for you. I'm not going to write any more of my own words unless I see one of you write it. Maybe I'll just draw a picture, though, to inspire us. Here's x. Here's f of x. Here's f. And then I began with let O be any open cover. So that means... Sorry, I should say, this is important. I'm trying to show f of x is compact. So O is any open cover of f of x. This is a little confusing. Right? So it's an open cover over here, not on the other side. It's an open cover of f of x because that's what I'm trying to show is compact. So we have a bunch of open sets covering the whole thing. One really big one. All right. And you want to think about what can you do with those things, knowing all you really know is, well, x is compact and f is continuous. You want to think about, what do I like to do with a continuous function? I know what I like to do. Not a bad idea, although I would say with a continuous function, I don't actually like it. Because
you open and
definition
select f of x implies
but that actually
inverse of u is open of x. Is that what we're saying?
you're starting yeah. Well, if you bring it back here, first of all, it automatically will cover all of them. Well, no, not even. So like, you have to use one of the sets of it. And back here, it's so many sets of it. Yeah, but then X is compact, so you can make it finite over here.
Well, like, forget about the compact, like, part of it, you know that, like, any open set in f of x is continuous is open in x.
I think it's the u open f of x.
And
Yes.
F inverse u.
If O is a
But what does that tell us?
Continuous function
Made
here
up
are
of
measurable. Remember the definition?
Oh, O is an open set. O is open in f of x.
Set is open set. So that means it's open.
Yeah.
Right.
Which means,
Right.
which probably means it's finite, I guess.
Ideas?
So I think well, if it's open, it has to be. Or no, if it's open, it can be infinite though. Because isn't all.
All right, I saw somebody say something good. I'm going to say for each V in the open cover, these are like the V's. You know, you could say V1, V2, whatever, but I wouldn't say that actually, because there may not be finally many of them. In fact, there could be uncountably many of them. But anyway, these are open sets over here, and since F is continuous, you can pull them back over there. That's the definition of continuous, remember, is that F inverse of whatever. So for each of these, F inverse of V will be open in X. So those blue guys over here, they create a bunch of little blue guys over there. Or they don't have to be blue, I suppose, but these little guys, right? They come from pulling all of these sets back to over there. Yeah. That's the first step. I'm going to keep walking around.
Did
you have this idea?
It's open max.
Cover is equal to but what if it's not going to 1 by 2? That box can be smaller than the access.
It's not. So all the sets over there, they make an open cover for X. I think it's not. I don't really care if it's.
No, but like, how do you know that? Like, what if after box has like a smaller open cover? Maybe. I guess I don't know how.
It's like however many sets you have over here, you get the same number of sets back here.
But how do we know they're all covering? Like the,
How do we know they're all covering X?
Yeah.
Because every point of X, when you do F to it, lands in F of X, which means when you pull back any point inside F of X, it has to be part of X. Yeah. Some people said, I think this is, maybe you saw this is where I was going with the picture. If you pull back all of those sets, then they make an open cover over here. You end up covering up all the points of X over there. See where that gets you. Mm-hmm. Yeah, that's the idea. I saw some people saying, since X is compact, that means these guys, when you pull them back, there's actually a finite subcover over here. And so maybe I'll write this. I don't know if you're writing with the same notation as I am. How about F inverse V1, F inverse V2, right? F inverse Vn. Only finitely many. This covers X, right? Yeah. Can anyone say out loud where we're going with this? Remember, the end game is to show a finite cover over here, right? This is where we're supposed to end up. Can anyone want to suggest? What should I use to cover this using only finitely many sets? Yeah?
You have to go back to so wouldn't you take F of all of those?
Yeah, do f of all of these. Yeah. And what is that? Actually, you can say very, yeah, it's just v1, v2, up to vn. That covers f of x, which is finitely many as a finite subcover, right? That's what we wanted. Yeah, that's the idea. So you just apply f, and that means v1 Is that really a subcover of what I started with at the very beginning? Or have I changed the sets by pulling them backwards and then pushing them back forwards? Something to think about. I think actually these are the same sets that I started with. These V's are, you know, where they came from was I just pulled back the original sets. So these V's, they are some of these original sets. And there's only finitely many of them. Yeah, that's how we do it. Great. I hope that that makes sense. You know, you have infinitely many over here. You bring them back here. There's still infinitely many of them, but since X is compact, you only need to use finitely many of them. But then you choose those same finitely many of them over here, and that is your finite subcover. Yeah, great. We got about 5 more minutes, but I think, you know, the other thing that I wanted to talk about, I think maybe we can leave till next time, if that's all right with you all. I'd be happy to hang around and chat about the homework if anybody has more homework questions, but maybe we'll leave it at that for today.